Okay, so later I will give you the example for the cross product, but before that, let's see the property and for its cross product, let's see the property. So yeah, so actually we have this result. If you want to know for this vector, the cross product of A and B, the relationship between its cross product and A and B. You want to know their relationship. Actually, we have this result. The cross product is orthogonal to A and also orthogonal to B. Also orthogonal to B. Yeah. So and actually we could check it. We check some. If we consider when we consider, if we want to say these two vectors are orthogonal, what do we need to do? Orthogonal means that you should show that the inner product equals 0, right? So we consider the inner product. Actually, we consider the inner product. So this one is the A cross B, the inner product, the vector is this one. A cross B, the vector is this one, or this one. And A I could write down here A1, A2, A3. So when we consider their inner product, so first coordinate is A1 and this 10. So we write down A1 times A2B3 subtract A3B2. It's the first coordinate of their cross product, and plus A2 times this term, so it's A3B1. A3B1 subtract A1B3, and the next one is A3 times the last one A1B2 subtract A2B1. So let's see. So yeah. So so if you calculate, you will see it's equal to A1, A2, B3 subtract A1, B2, A3 plus A2, A3, B1 subtract A1, A2, B3 plus A1. Yeah, here plus A1, A3, B2 subtract A2, A3, B1. And here we could cancel some, right? A1, A2, B3, A1, A2, B3, and we still have another one. A2, B3, B1, A2, A3, B1, A2, A3, B1, and so on. A1, B2, A3, A1, B2, A3, and so on. So actually it's equal to 0. Yeah. So indeed, these two vectors, their inner product equals 0 means that they are orthogonal. Or you could use this notation. Means that they are orthogonal. Yeah. And of course, if you check this one, their inner product is the same as we say for two vectors. Their inner product, if you consider the inner product of these two vectors, this one and this one, by definition is the same. All of them equals 0. Yeah. And for the vector B, you could check it will be similar. So you will see that these two vectors, their inner product also equals 0. It also means that it's orthogonal to the vector B. So indeed, the cross product of A and B is orthogonal to the original vector A, and it's also orthogonal to original vector B. Yeah. So it's their relationship. So by the relationship, we could say more. So for the cross product now, we could characterize the cross product of two vectors A and B. So I write down some information here. So for the cross product A and B, their cross product, if we want to characterize this vector, we have two properties we should mention. There are two properties we should mention. First one is the direction. direction. So as we know, we have a vectors A, we have a vectors A and a vectors B. And what's the direction about A cross B? It's orthogonal to the vector A, and it's also orthogonal to the vector B. So for these two vectors, it could span a plane. So if the vector is orthogonal to A and B, then it also orthogonal to any vectors in its spanning set, in their spanning set. Yeah. So the direction is something like that. Here this one is called right hand rule. Right hand rule. Here we have, you could view it this way. We have 4 fingers pointing in the direction A, and we rotate it to the direction B, then your thumb points in the direction A cross B. So your thumb points to the direction A cross B. Point to the direction A cross B. Yeah, so it's orthogonal to A, it's also orthogonal to B. So you will orthogonal to any plane which contain these two vectors S. You will orthogonal. If we have any vector V in the plane S, then will be orthogonal. A cross B is orthogonal to any vector in the plane V. And it's called right hand rule. Probably some of you have heard this one before. Okay, anyway, so and for the cross product A and B, their cross product, it's the direction. And for the magnitude, or you could say it's length. The length. What's the length of their inner product? Their length. Actually, their length is the result is this one. Cosine theta. Cosine theta is, yeah. Here is sine theta. Yeah. Theta means their degree, their angle. Their angle is theta. Yeah. So and if you want to check its detail, it's in page 560, and it's Serial 6. Yeah. Okay. Yeah. So it's about the direction, it's about the magnitude. And so we have a quick corollary here. We have a quick corollary. First one is the vectors. If we say two vectors A and B, they are parallel. Then what can we say? Use this one, magnitude, because here. Okay, so here I should say more. Here, what does it mean? Actually, you could view it this way. It's something this one. I erase it here. We have a vector A, we have a vector B, right? And it's the theta, angle theta. So, what's the value mean in the graph? You could see in this way. The length is exactly the length of AB, and when we consider the right triangle here, then it's a hypotenuse. Hypotenuse is A. The angle is theta. So opposite side is exactly here is exactly sine theta, right? So when we consider the value, it's something like this one. It's like this one. We consider parallel grain. Parallel grain. This parallel grain, its area, it's exactly equal to the length times the length times its length. Right? The area about this parallel grain, its area is exactly this one, and it's exactly this one, right? It's exactly this one. So it's exactly the length of their cross product. So for the cross product, its length or its magnitude, it's exactly the area of this parallel grain. Okay, so first corollary, if two vectors are parallel, then of course their area, this area, of course the area equals 0. The area equals 0. And in this case, it also means that the area is, the formula about area is this one. And if these two vectors are non-zero, then it means that sin theta equals 0. Sin theta equals 0. Here is our vector A, our vector B. Sin is the angle B, the angle theta. So sin theta equals 0 means that theta equals 0, right? Or 180 degrees. So it means that they are parallel. And we could use this notation. Parallel. It means this one. They are parallel. We use this notation. Yeah. Okay, so let me see. Yeah, so of course it also means that A their cross product equals 0. Oh, then yeah, it's the same. And then let me remind you, if we say two vectors A and B are orthogonal. What do we mean? It means that its definition is this one, right? Scalar product equals 0, and it also means cosine theta equals and we know that cosine theta equals this one. Yeah, so in this case cosine theta equals 0, so it means in this case theta is 90 degrees. Yeah, two vectors. So you could see that you could compare with these two results. It's different. For scale inner product and for cross product, they mean different things. Okay. Yeah. So now we could consider one more example. So I erase it. No, we can see. Now I will give you one example. So we could find in chapter 10. You should know I will ask you the questions. I will give you I will give you three vectors in R3 space, and you should know how to characterize this plane. The plane which contains these 3 points. I will give you 3 points in a plane. If we have 3 points, then we could generalize a plane which contains these 3 points, and you should know how to characterize this plane. Yeah, but it's relative to this one. So, and I will explain it later. Okay, so for this example, we want to find a vector perpendicular to the plane passing through these 3 points, P 146, Q negative 2, 5, negative 1, R 1, negative 1, 1, PQR. Okay. Yeah, so we want to find a vector which is perpendicular to the plane, and this plane pass through these 3 points. Pass through these 3 points. Okay, and actually for this vector, later we will define it. It also means that it's normal vector. It's a normal vector of the plane. It's normal vector of the plane. Normal vector of the plane. It's called a normal vector of the plane. Yeah. Okay. So we will use this one. As we say, if we have 2 vectors, and for these 2 vectors, once we consider their cross product, then the cross product is orthogonal to original vector A, and it's also orthogonal to original vector B, right? They are orthogonal. So it will orthogonal to any vector in the plane which contain these 2 vectors. But now the plane contains 3 points, not 2 vectors. So what can we do? We could construct 2 vectors, right, in this plane, right? So here we have a plane, and we have the vector here. We call it P, and we call it Q, and it's our R. So we could consider 2 vectors. One is PQ, right? Of course, you could fix another point. For example, you could choose Q and consider QP, QR, or fix R, consider RP, RQ. Okay, so here I just fix the point P. So I consider PQ and the PR and the PR. And what's the PQ, PR? I write down 10 by 10. So PQ, so P is the initial point, Q is the terminal point. So terminal point subtract initial point. So Q subtract P. Q subtract in first coordinate Q subtract P. Second coordinate Q subtract P. Third coordinate Q subtract P. So it's exactly negative 3, 1, negative 7. And then it's for the vector PR. PR here is 1 subtract 1. Negative 1 subtract 4. Negative 1 subtract 4. 1 subtract 6. 1 subtract 6. So finally it's 0, negative 5, negative 5, negative 5. This one. Okay, so actually the plane, the plane which contain these 3 points is, if we call it S, then these 2 vectors is exactly in the plane S. Yeah, so use these 2 vectors, we could consider, if we want to find a vector perpendicular to this plane, or you could say perpendicular to these two vectors, then you could consider its cross product. So now we follow the definition of our cross product, and I write down here. So we consider the cross product. So now we consider the cross product, PQ, PR. So cross product, and here we use the notation I, J, K, and the PQ is negative 3, 1, negative 7, and 0, negative 5, negative 5. Here, and here, I remind you, I is 1, 0, 0. It's exactly the E1 vector in linear algebra, and it's E2 vector 0, 1, 0. K is 0, 0, 1. E3 vector. Okay, so yeah, so by the definition, you could see here is our I and J and K, and I, J, K here is positive. Here is positive, negative, positive, and positive, negative, positive. Yeah. And I, we consider the 2 by 2 submatrix its determinant. So it's 1 times negative 5. 1 times negative 5. So it's negative 5 subtract negative 5 times negative 7. So it's 35. 35. Oh yeah, here I write down 2 by 2 is 5. 1 times negative 5 subtract negative 7 times negative 5. Here. And this one is consider these two columns and their determinant. Negative 3 times negative 5 subtract 0 times negative 7. And the last one in the determinant. Negative 3 times negative 5 subtract 0 times 1. Okay. So now we could change 10. We could change 10. So it's negative 5. So it's positive 35, but we subtract 35, so this 10 becomes negative 5 subtract 35, so it's negative 40, and here is 15, and here is 0, so it becomes subtract 15, and here is also 15 subtract 0, so it's still 15, so finally it's negative 40. It's negative 40i subtract 15j plus 15k. So it's negative 40, negative 15, 15. Yeah, so it's exactly the vector what we want. The vector what we want to find. And for the normal vector, sometimes we denote it by n, so we could denote it by n. Then the normal vector, as we say, of course, it's orthogonal to the vector PQ, and it's also orthogonal to the vector PR. So, of course, it will orthogonal to any vector in S, and S is exactly this one. Okay. So it's an example what we want to figure out. It's the vector which is perpendicular to the plane passing through PQR. Yeah. Okay. Yeah. So for this one, actually in next section we will talk about now once we have the normal vector, we could characterize the plane S. What we want to solve is to figure out the plane S, which contain these 3 points. We want to figure out the plane S. So now once we have the normal vector n, then we could figure out the plane S. Yeah, this part. Yeah. So next topic we will consider this one. Okay.